Okay, so let's start this webinar, this episode. This is the number 3 episode of Your Personal Trainer series, and this is a special series created by me and Alessandro Tornincasa, focused on let's say deepening the experience, deepening the learning on a specific product like simulation and so on. In the first 2 episodes, we have seen some tips and tricks about simulation and flow. And in this episode, we will check, let's say, more in-depth research and development tools inside simulation and flow simulation. Here with me, it's Alessandro Tornincasa. Alessandro, are you there? Alessandro?
Yes, hello, and welcome everybody to this webinar.
Okay, perfect. So, some words about the webinar tools. Of course, as always, the webinar has been recorded right now, so you will receive also a link to review the webinar in some days if there is some problem on the line, on the slides or the audio. So don't be afraid. You will receive this link to review it later. I prefer if you input already question when you have, because we are in queue, so we can easily answer your question in the middle of the webinar instead waiting to the end. So let's start. Here it's the episode installments. The first 2 episodes, like I said, they were about simulation and flow simulation tips and tricks. If you want, you can write to me or to Alessandro to receive the link to review them. And this webinar is about research and development tools within soil simulation and flow. And I would like Alessandro also to speak about the next episode.
Okay, yes. The next episode will be about workflows from design to manufacturing. We will use a case study of our customer Urban 626, who designed a very innovative vehicle for urban mobility. And we will show how with the SOLIDWORKS product portfolio you can start from the concept and go very, very quickly to manufacturing with innovative technologies like MBD and additive manufacturing.
Okay, thank you. So a little bit about ourselves. I'm Alessandro Bellini. I'm the simulation specialist for EUROMED. With me also Alessandro Tornincasa. And we, let's say, agreed on this term. We are the simulation team. It's not official, but it's just a nice, let's say, team work we have in place. EUROMED means Italy, of course, Balkans, Greece, Turkey, and Israel as well. So let's start from the design of experiment basics. So the basics of the approach for the optimization scenarios and tools that we have in simulation. Then we will see what is the what-if scenario in flow simulation and the optimization in flow simulation. Then we will jump on simulation and we will see the same stuff, so optimization or let's say design scenarios and optimization in simulation. And we will finish with the topology study in simulation, that it's new for 2018, but also there are some new features in 2019. So let's get started. The first slide that I would like to share is about the manual approach. When you are designing something, a product with, let's say, some parameter in mind, of course, you can optimize manually something, but there is a risk. The risk is to optimize only one step at a time, and this can lead you to, let's say, an apparent maximum, an apparent optimal. So you are just optimizing one factor at each time. And so the risk is to go, let's say, near, but not so near to the real maximum or minimum. So the real optimization, optimized model or product. Okay, and also this is a manual approach. In terms of simulation and flow simulation, instead you can use another approach that it's modern in terms that is in contrast to manual, but in reality, design of experiment is a very well studied and steady approach with, let's say, for many years. Basically, this is the standard in the market for this kind of stuff. And the idea is to change several factors simultaneously, but not to try all the combination, not to try all the linear combination of the parameters. So you can have, let's say, both the benefits of optimizing parameters, more than one, and to define a goal to reach the best design. Okay. And we will see in a moment what you can use inside simulation and flow simulation. Of course, the approach here is to use simulation as a design tool. So after the concept phase, immediately you can start with simulation or flow, even in 2D. I don't know if you know this, but you can use it directly in 2D simulation and flow. So you can start immediately to evaluate your concept, and if you have issues, you can easily and very fast analyze it in design scenarios or optimization study. So you have the ability to quickly reach your objective. Okay, let's talk about what is Senario in flow simulation, and I will change the presenter to Alessandro. Alessandro, are you there?
Yes.
Okay.
Perfect. Can you see my screen?
Yeah.
Okay. So we will now talk about the what if scenario in SOLIDWORKS flow simulation. During the last episode, we already seen how you can optimize with SOLIDWORKS simulation solutions by creating configurations, comparing them, and be able to determine what is the best design. Flow simulation, what if analysis, is a very convenient way to automate and speed up this process because it's a tabular interface that allows you to change the model dimensions, for example, the whole dimension you see in the picture, or a boundary condition like a flow rate or a pressure. And then when you're finished changing your model or planning the change, you can run all the studies in batch mode. And finally, you can, in the same interface, you can do simulation comparisons. So for example, for a lamp, you can see what is the thermal performance as a function of a lamp angle. So how do you run a what if study? The first step is defining the input variable, so what you want to change. Second step is defining the output parameter, so what is the result you want to monitor. For what concerns the input variables, you can change SOLIDWORKS model dimensions. You can also leverage on design table parameters. And also you can change boundary conditions like flow rate, pressure, but you can also modify general settings, for example, initial conditions or even mesh settings if you want to use this table to optimize your mesh. About input variables, there are some ways to define the variation, because before running the scenarios, you have to define how many scenarios. So in this case, I'm changing a dimension and I'm defining 4 cases. One method is using discrete values. So you just input your the single values in a tabular form. A more convenient way is the range with numbers. So it means that you define the minimum, the maximum value of your interval, and the number of scenarios. So flow simulation will figure out what are the values, the 5 values that will have to be studied. You can also use a range width step, which is very similar to the previous case. You just define minimum, maximum, in this case the interval of a range, and flow simulation will figure out that you will need 6 cases. The final way is the step around. You define let's call it a central value, and then an interval size. In this case, it's 10 millimeters, and then how many intervals you want to go before and after that central value. So in this case, I'm choosing 100, and I want to go back 4 intervals and forward 5 intervals. And you see in this picture the values that were figured out by flow simulation. For what concerns the output, you will surely use the goals as an output parameter. In this case, a goal is just used as a quantity to monitor. So you, for example, you define a pressure loss. It will be what you want to monitor as the dimension is varying. And another thing you can compare or vary is the cut plot. So you can see, for example, what happens to velocity, pressure by displaying the cut plot on a static image. But also you can use X, Y plots, flow trajectories, all the results that are available in flow simulation. So the steps, so just to summarize, it's 3 steps. Your variable, what you want to change, in this case, a dimension. What you want to monitor. In this case, I'm monitoring the pressure drop as a goal, for example, as an equation goal, a cut plot, and then flow trajectories. And then the final step is running the scenario. It's a tabular form that will show you all the cases that you're going to study, and then you can set the solver options, like how many cores you want to use, if you want to close the solver monitor. So let's make a practical example of this approach on this valve. The fluid is air, the inlet flow rate is known, and also the outlet pressure. And you want to find out what is the pressure loss as a function of the dimension you see the picture. The more the valve is closed, the more there will be pressure drop, and we want to see how much is it as the dimension becomes smaller and smaller. So first step is creating the parametric study. You go to the flow simulation study and choose new parametric study. And then there are 2 options: goal optimization, which will be covered later by Alessandro, and what if analysis, which is our case. So you choose the icon add dimension parameter. The other icon is when you want to vary boundary conditions. Then you click on the dimension to capture it. In this case, it's the opening dimension of the valve. And then you edit the variation. In this case, will be some discrete values that don't have a particular relation. After you've done that, your input is finished. So it will be 4 scenarios that will be studied. For what concerns the output parameters, we will choose a goal. So we will click on add goal, and we will use the pressure drop goal, equation goal that has been previously defined. Then also we can monitor other plots. So we will add, for example, the flow trajectories and the cut plots, so that we can compare all the scenarios also in a graphical way. When we're finished with this, we are in the final stage in which we can run the study and define the options. So in this case, we have chosen to close the solver monitor after each study is run, and then we will use all the cores of the machine. So this is what happens when you run. The first study is run, and you see the preview of the results in the solver monitor. The second one is run, and then finally the last 2 studies. As the studies are running, you will see a green background showing what studies are finished. And also in the line showing the pressure drop, you already have your final result. But you also have some advanced tools to analyze your results. Let's see an example here. You can click on the cut plot, and the flow simulation will show in one interface the pictures of the cut plots for the 4 cases. But also you can have a look at the min and max values of this pressure drop directly from this interface of the max pressure that was derived from the cut plot. And then you can also have a look at the goal plot. Here we see the pressure drop value for the 4 cases, and you also have some controls to make some analysis on this data without having to go to Excel. So you can compare the minimum, the maximum, see what is the relative difference between the values. And also you can have a look at the values in a tabular form or in a graphical form. For example, this is a history plot of the iteration. Or you can also have a look at this chart that shows the pressure drop as a function of a dimension that was varied. And this is really very convenient. So you see that as the dimension becomes smaller and smaller, there is more pressure drop. Obviously, you can also export the data to Excel so that you can elaborate as you want, and you also get an automatic plot in a histogram form. So as you've seen, it's a very easy interface. You don't have to create configurations. Flow simulation will make the job of changing the dimension. And this way you can identify if there are some interesting trends and take some design decisions based on those trends. And finally, you can automate result comparison because you do it in the same easy interface. Okay, so now I will leave the screen to Alessandro because he will show us a practical case of a customer that used this what-if analysis to optimize his design.
Okay, thank you, Alessandro. So here, I think one of the best benefit here is the fact that we are inside the SOLIDWORKS environment directly, and also it's automated. So you are not dealing with a lot of Excels or cut plots in JPEGs and so on. It's a convenient all-in-one interface that you can use. And in this case, I would like to show that one of our customers in Italy, the Dometic, has used this kind of approach for dealing with this kind of project. And they are producing air conditioning system for campers. And in this case, they have used the what-if scenario to explore the alternatives of an actual solution. So there was already on the market product, and they were intended to optimize that product. So in this case, I can show you this video, and I can talk about what they've done. Basically, it's a filter for the air intake. So there is a porous media, there is a fan, but also there is an idea of changing or enlarging or positioning in a different way the intake itself. So you can see that the design points in the what-if scenario, and this is, of course, ran automatically, are changing the position of the inlet. So you can see here in the middle. And automatically, in flow simulation, you can have the flow rate at the output. So in this case, an already analyzed product and already on the market can be optimized in a very short time. So after sometimes you can get the results, and I can skip to the final presentation that they presented to the internal managers, and they evaluate this kind of, let's say, ideas, this kind of different ideas that they had on this already on the market product. So they explore the inlet as is, the left inlet, a larger inlet, central inlet, and the right inlet. And this is the slideshow from directly from Dometic. Basically, they reported all the cut plots and flow trajectories and the values, and they discovered a very interesting thing, because in the end, this is the last case. So in the end, they discovered that the larger, let's say, model approach was dealing with a more enhanced airflow. So let's say versus the already on the market project, they discovered that they had a very large increase in this case. So very good, interesting case for flow simulation. Also, I would like to talk about Radiatori Aluminium in Romania. RAL is also a client in other countries as well, and they are dealing with the big radiators for automotive industry. And in this case, also flow simulation has been used very efficiently to reduce time and cost about prototypes, because they have a laboratory inside the company, but it's costly to have a lot of prototypes, and also takes time. So in this case, they have produced a lot of design scenarios within flow simulation, and they have discovered a better way to deal with this kind of dimension on the radiator itself. So very convenient for this company. Okay, so let's go on the next will be optimization in flow simulation. So we have talked right now about what-if scenarios. So let's say a manual approach, automated. Okay, so basically, I'm in input. I have a lot of design scenarios. Basically, instead of running them manually, it's the flow simulation that is doing automatically. But now we would like to have another step. We would like to have an optimization. So we would like to drive the simulations with a goal in mind. For example, the flow rate of a gas, or the dimension of the diameter of a conduit. So something like that. Also, we can use it model dimension to do that, and we can use it more than one in the design of experiment approach in flow simulation. We will see both. So what is the start? The starting point is to change an input, a variable, a parameter, based on a range. Then we can set a target, a value. So in this case, it's not only to monitor, to check, to have a sensor, but also to have a target to achieve, if it's possible, of course. And then we can automatically have the best design, the best product in this sense. So it's very convenient for more than one reason. So three easy steps. Basically, we have to define variables, parameters. Can be, of course, parameters inside the product. So again, as a diameter, or a thickness, or something else. Or it can be also something inside the analysis. For example, a pressure drop, or flow rate, and something like that. We have to define a criteria to define the goal. So basically, a target and a deviation. So in this case, 10 bar pressure plus or minus 0.5. So we can have a deviation from the target that we want. And we can set up the scenario. Let's say, optionally, we can also have some other parameters for output, to have, let's say, some other sensors to make comparison. Okay, let's talk about this example. Very simple. We have a valve. It's a pressure valve. So in this case, we would like to understand, with the inlet pressure of 12 bars and this kind of flow rate, we like to understand what is the outlet pressure. That is, let's say, an easy task, but we can do it with flow simulation automatically. For doing this, we will have, let's say, a reverse approach we will see in a moment. So the solution is to put a flow rate as an inlet. Of course, we have a fixed flow rate. We have as an outlet an environment pressure. The environment pressure tells the software to run with a fixed static pressure, but to calculate the dynamic pressure. This is very convenient for our goal. So we can put one goal to monitor the inlet pressure. So that's why I've said it's a reverse approach, because we are varying the inlet pressure to check what is the outlet with this kind of flow rate. Okay. Let's say that manually we have to run many studies to do that. Okay. But instead we will use an automatic approach, because with the goal optimization we can ask to find the optimal solution automatically. Let's check how it's done. Basically, we have the goal optimization here. So we have to select the goal optimization. We have the environment pressure that is ranging from 1 and 11. Of course, that is an educated guess because we know something about our product, of course. Of course, we can also extend the range, but in this case, it makes no sense. We have a criteria to reach. So the pressure at the inlet is 12 bar. So we won't like to have this kind of inlet pressure. And of course, we have to run a scenario, that is the goal optimization scenario. We can define a limit for the number of calculation. We can define how many cores, if we want the full results, and so on. Okay. So basically, to summarize, this is what to change inside analysis. This is what to monitor and to achieve, and this is and those are the options for the run. So again, we choose goal optimization instead of what if analysis. In 2018, we will also extended the features in flow simulation, and now we are able also to optimize multiple parameters. In goal optimization, we are able to optimize only one parameter. We will see also the multi-parameter approach in a moment. So we can add the simulation parameter here. Very simple because it's an already input boundary condition. So we have 1 bar and 11 bar as limits. And we have a goal. Now the goal is not only a measure, it's not only a sensor, it's really a goal that we want to achieve. This is the target value, 12 bars, and 0.2 bar is the precision that we would like to have. Okay. So we have to click run, and this is the simulated analysis. This is at full normal speed. Basically, we can see that the parametric study, the goal optimization study, is running the design scenario that he tends to understand that it needs. So it doesn't run every single calculation. So in this case, we have seen that we have 11 values to check, and the optimization have run only 3 design points. So it's very convenient because not only we have achieved an optimum value, we can see here we have achieved the pressure inlet as 11.99, so very, very near to the 12 bar that we want. But also we saved a lot of time because he ran only 3 design points. So the solution is converged and we are very happy. So let's talk about also the goal optimization with multi-parameters. In this case, I would like to share this exercise. It's an example about the design of experiment inside flow simulation. So in this case, we are setting up, there is a collector with 3 porous media, 3 filters, and 3 valves. Here you can see also the angle of the valves, and of course an output. So we'd like to achieve, let's say, a very steady flow at the outlet with this, with the flow rate in mind. How to achieve that? Basically, we have three input variables. Those are the angles of the three valves. So ranging from 0 to 60 degrees. Of course, this is a continuous range. So we are not defining steps. We are just defining the continuous range for each valve. And this is very interesting. Also, we have set up parameters for output. This is not the goal. It's just parameters that we want to use in a goal function. We'll see in a moment. So the tree flow rate and the pressure drop. Basically, here we have to define an objecting function. An objecting function is very interesting because it's kind of not too much complicated. We have the tree flow rate that you want to achieve, the target for each that I've set up as 20 kilogram per second for each of them, and the weight. The weight is the importance, the priority that we want to have on each flow rate. Also, we have a pressure drop as a target 0. Let's say it's impossible to have 0, but it's to tend to that kind of target. But the weight is 1/10 of the others because, of course, we know that this kind of target is not, let's say, so realistic. So we would like to have this, but the most important approach is to have 20 kilogram per second for each flow rate. And of course, you can maximize, minimize, or search for a target value for all these kind of equation and functions. Okay, so running, let's go directly to the point here. So this is the starting point. Of course, you have to set up an analysis. After that, just let me skip to the point. Okay. After that, you can define the design of experiment. You can see here the three valves and the 4 parameters that we have set up. So we have the scenario here, it's already ran, and you can see that we have 31 experiments. So imagine to explore all the combination of the valves angles from 0 to 60. Of course, it will take a lot more than 31 experiments. So basically, here is the beauty of the design of experiment approach. It's defining only what this is needed, okay? And we have the optimum values. So you can see that we have 20.3 for the first flow rate, 19.2 for the second, and 20.4 for the third. So very, very close to what we expected. And a pressure drop of 280 pascals, so not bad. So this is the power of design of experiment in flow simulation. So benefits: automatic iteration, automatic run, no manual iteration. Of course, we are speaking the designer language. Why I'm saying that? Because we are defining what we need as engineers, as a designer, and what is the need of the product, okay, the goal of the product. Also, we automatically determine the best in a very large amount of cases, okay? So let's talk about now the design of experiment and optimization in simulation with Alessandro. Alessandro, are you there?
Yes.
Okay, I'll change to you. Okay.
Okay, thank you very much. So now we will see the same approaches you saw for flow simulation applied to SOLIDWORKS simulation. So we will see what is called design scenario, which is very similar to flow simulation what if study. You change the parameters and then you see what's the variation in your results. And then the other one is the SOLIDWORKS simulation design optimization. So the software will figure out automatically what is the best design by changing model dimension and finding the best compromise between reducing weight and getting performance. So what is a design scenario? It's again a table in tabular interface where you can change dimensions or again boundary condition, which can be a force, a mesh parameter, can be a prescribed restraint. The table allows to launch several studies in batch, and then you can monitor what's the variation of results as a function of the parameter change. So you need two steps for the design scenario. First, your variable, what you want to change. And second, in the software is called constraint, but actually is not a constraint, it's just the parameter you want to monitor as the variable is changing. So for example, you are monitoring the stress, so how the stress is changing as a function of the thickness. The name constraint comes from the fact that the same interface is used for optimization, and in optimization, the stress is used as a constraint to limit the maximum stress. So the variables can be SOLIDWORKS dimensions, or can even be global variables if you're doing you're pushing your model parameterization with equations. It can be boundary conditions, for example, a single material property, a force, prescribed restraints, mesh, contact parameters, bolt, preload, for example. Or if you have SOLIDWORKS Simulation Professional or SOLIDWORKS Simulation Premium, you can even vary material for each case and compare how the results are changing as you're changing your material. So the methods to define the variables are this. First, discrete values, as before, you just digit the values separated by comma. Then you can use a range with step. You define the minimum, the maximum, the interval, and then the software will figure out how many scenarios to study. In this case, you're going from 5 to 15 with 1 millimeter step, and it's 11 scenarios. And also, you can use a range, but not in design scenario. The range is allowed only in optimization, which we will see later. So the constraint can be, basically is a sensor. So you can define a sensor that monitors stress, strain, displacement, or for example, frequency. Then you decide for example, what stress component you want to monitor. Can be von Mises, can be stress intensity, and so on. And also, you can define the sensor location. So not only you can monitor the model max, but you can also monitor the stress on a particular location. And if the sensor is based on a transient study like dynamic study, you can concentrate on a particular time step or check the maximum across all time steps. So it's two easy steps. First, your parameter, what you want to change. In this case, it's a dimension. Second, you define your constraint, what quantity you want to monitor as the dimension is varying. Let's make a practical example. You have this structure with a fixed constraint and a force. The material is IZ304, and you want to see what is the stress and displacement variation as you change the thickness you see in the lower picture. So first step is adding a variable. You create the design study, and in variables you choose add parameter. After that, you will get this window, and here you need to name the parameter. In this case will be thickness, and define that it's a model dimension. Then you click on the dimension, and it will be captured by SOLIDWORKS Simulation. After you've done this, you need to define the variation. In this case, it's a range from 5 to 15 millimeters with 1 millimeter amplitude. And if you have multiple parameters, say you want to change the thickness, but also the 20mm radius, in this case, the software will figure out all the possible combinations. So in this case, if you combine a variation of 5 to 20 for the radius and a variation of 5 to 15 for the thickness, you'll get 44 scenarios. Then you have to add the constraint. If you go on constraint, you will get add sensor. In this case, we don't want to monitor the max stress, but we want to monitor the stress in X direction on the central vertex you see in the picture. So we need to choose max over selected entities and click on the vertex. After that, you need to choose that you want to do monitor only. The other options you see are for the optimization where the constraint is a real constraint. In this case, we are just using the sensor to monitor the quantity. And then you need to choose what study you're referencing, because you could have many studies, and in this case, we're referencing the static study and not the nonlinear study we already have in our model. This is the interface, will be very quickly to run. It will solve each study. The table will be populated, and in this table, you will get in real time the results for stress and displacement in a tabular form. So very, very quick. And also you get the visual update of a model. So when you're reviewing the results, when you click on one scenario, you will see the stress and displacement value, but also the plots will update in the graphics area. You see, I click on the second scenario and the thickness has increased, and then on the third it's increasing even more. One thing that is very interesting is having a look at how the variation of the thickness is influencing the stress or displacement. So you use a history plot. After you choose that, you need to put on the y-axis the constraint, so the parameter you're monitoring, which is stress. And then you can create plots like this. In this case, on the x-axis, there are the scenarios you've defined from the smallest to the biggest thickness, and the stress value. As you see, the stress is gradually decreasing as the thickness increases, and the same for displacement. Maybe if you don't like on the x-axis to see the name of the scenario, you would like to have the thickness, you can export this plot to Excel, and here you can elaborate it and maybe change the order of the data so that you can see the stress based on the part thickness or the displacement as a function of a part thickness. You see that there is a very big decrease of stress and displacement as the thickness is increasing. Should be a cubic trend. So the value of design scenarios is that you can, in one interface, you can plan your changes without even touching your model, and you can show very easily to other designers the impact of that change. So the trend will be used to take some decisions on your design. And this automation will give you the value because you can spend time on more important tasks than just changing manually the model. Okay, now we will see the other approach, which is design optimization, which is very similar to flow simulation parametric study with goal optimization. In this case, we can change again a parameter variable, but this time we're not using any interval, we're using a range. So for example, I will define a variation of my parameter from 3 to 9 millimeters, and then the software will figure out how many cases to study. Then in this case, we will need to put a constraint. Very often you put a factor of safety limit or a stress limit that you shouldn't exceed. And then there will be the goal, because obviously there could be infinite cases where the constraint is honored. The goal is used to define what is the best case, and usually the goal is minimizing mass or maybe having a certain frequency range. So the steps are the same as before, the variable. This time the constraint will have a condition. So you will define a sensor, but there will be a condition like stress should be less than 140 megapascal or between certain values. And you will have to add a goal. So this will be used to choose the best design. In this case, for example, you can use minimize mass or maximize surface area for example, for a thermal study, or is exactly, which is very typically used for frequency studies. Let's make a practical example. In this steering bracket, you have a fixed constraint at the back, you have a side force, and you get this stress results. And you want to optimize this design by reducing the mass while keeping below 150 megapascals. So this is the table that defines the conditions. As you see, we are changing the 12 millimeters, the 5 millimeters thickness, and we have two fillets which are 12 millimeters radius. And we are using just a range. As you see, the thickness is from 3.5 to 5, and the fillets are from 8 to 12. I don't define any number of steps. They will be figured out by the software. And then there is a limit, which is 150 megapascal stress. So the parameters is what we are changing. What is required is the constraint. And finally, what is the goal? In this case, we want to minimize the mass. The best design will be the lighter one. For what concerns the number of scenarios, you have to keep in mind that the more variables you have, the more scenarios there are. Because if you have two variables and each of them has 3 values, there will be 3 to the power of 2, 9 calculations to make. And the more of them you have, the more calculations. So if you have 7 variables and 3 values, you'll come out with 2,187 calculations. That's a lot. That's why the design for experiment approach will use a statistical approach to study only a set of those significant scenarios. If you go to customer portal, there is a solution. You see in the picture the number of solution. There will be a very detailed explanation of the algorithms used. Basically, if you use the high quality setting, you use the box Banken algorithm. If you use the fast result, you will use the Reichenhofer algorithm. This is the example. You run the study, and as the study runs, you will see some studies being colored in, some scenarios being colored in red, which are those that do not respect the constraint. The others in gray are honoring the constraint, while the one in green is the optimal. If I replay the video, you will see that the optimal one will be calculating only at the end of each scenario. So the optimal one is the one you see with the green arrow. This is the table, and we saved a lot of time, because if we had the 3 variables and 3 values, it would have been 27 calculations. While now, by using a range, the software only studied 15 cases. The more variables you have, the more value is in this design of experiment approach. And finally, it was a software to tell us the optimal solution. This is on the left, the original design, and on the right, there is the optimized design. Of course, the dimensions are not rounded, but you can change them. And one important information for you is that when you click on the optimal design, the model is immediately changed. So what you see on screen has already its dimension changed. You don't have to do anything. It's ready. Another interesting information you can gain from this study is a sensitivity plot, and you can use a local trend graph. Basically, it will tell you what is the impact of that variable on your final result. For example, you can create a local trend graph with the fillet dimension on the x-axis and the stress on the y-axis, and get a curve like this, where you see that there is a lot of impact on the stress if you have values like 10 millimeters. Okay, this is an interesting example I want to show you. This example is used by the application engineers of our partners when they go for simulation professional trainings at our customers. It's a press structure with a force and a fixed constraint at the base. A static stress study was run on this press, and the stress and the displacement was found out. And also a frequency study was conducted because there was a concern with vibration. In this case, optimization was used by combining more than one study. So you see on the left, there are some dimensions that are changed. It is 5 dimensions that are being changed. Then the constraints will be that the stress should be below 100 megapascals, the maximum displacement should be less than 1 millimeter, and then one sensor was put on at the center of the yellow plate, which should be less than 0.5 millimeters. And also the first frequency mode should be between 80 and 150. So you see it's very, very complicated conditions. And also the goal is minimizing the mass. So if you had to do this manually with manual studies, you will take probably days to find the optimal solution for this press. So the study was run, and this table summarizes the results. As you see, there are only few iterations, something like 12 cases that are chosen by the software. This is the original design, and this is the optimized design. You see it's lighter, the legs have to become wider. So this is really, really an interesting example of the power of design optimization. Okay, so, and the final remark is that there was almost a 20% weight reduction. So I think I will summarize the benefits. As you saw, the range allows to automatically determine the number of test cases. So even if you have lots of variables, you will study only a subset. You can combine different study types, as you see, frequency, nonlinear, or dynamic. And this automation allows you to save time for more important tasks. So now I think I will switch to Alessandro, who will comment a real case of a customer in Serbia.
Okay. Can you see my screen?
Yes.
Okay. So thank you, Alessandro, for this part. Let's talk about this customer. Is in Serbia. It's Telsonic. I visited them some years ago. Also, I've had just some months ago about vibration analysis. They are dealing with, they are designing sonotroded, a special equipment to cut very precise rubber or plastics and so on. And they are designed to cut at a specific frequency. So the main design, the target is here is to design the product that is specific for an application. They cannot use, a customer cannot use the same sonotrode for different applications. So very customized design. And you can see on the right some of their design, and you can imagine how much work you need to define all the correct parameters, all the correct dimension in a stuff like that. So, for example, Telsonic use optimization study in simulation professional. This is an example of one of their sonotrode. This is the starting dimension, the starting picture, the start of the design. And you can see some dimension, for example, 50 from above the center of the slot, 30 from the bottom, 22 the diameters, and so on. They ran an optimization like we saw with Alessandro, and they find out an optimal solution. This was run in some minutes, let's say 30 or 40 minutes, okay, no more. So you can see something like 15 iterations, okay. So after that, you can check the resonant frequency that is very near to 20 kilohertz that you want, but also it's in the Y direction that is the most important thing that they like to have. And this is the final shape, very similar to what we saw. So imagine to find out this kind of dimension manually. It will be a nightmare, basically. Also, you have to produce something and to check it in a laboratory. So it's not very easy task. So in Simulation Professional, it's like automating this kind of approach, and in 30 minutes they can have the final solution. Okay, so let's talk about now topology study. Topology study is another form of optimization feature here in Simulation Professional and Simulation Premium. It's new from 2018, but also it has been enhanced this year. It's based on Tosca structure that is a part of Simulia family. So if you know Abacus brand, it's in the Simulia family. And it's in Simulation Professional and Simulation Premium. So we have developed this let's say, internally also with Simulia guys. And for now, only for now, it's limited to single part optimization. And this is based on the mesh instead of parameters. Let's check how it works. Basically, here you can see the head of a lacrosse maze. It's a game, so you can see the optimization of the mesh itself. Basically, you are not optimizing based on parameters, on dimension that you have set, but the software it automatically optimate the final shape based on the mesh itself that you have built inside simulation. Also, you can use preserved region or thickness control, we will see in a moment. You can have also a load case manager to assess multiple scenarios in one analysis. And you can define constraints to have, let's say, a more subtracting manufacturing form or ready for additive manufacturing. So let's check how it works. Basically, it's a module inside the simulation. You can see a setup of a static analysis, like you can do it in static analysis in simulation. And in this case, we are setting up a goal. The goal here is the best stiffness to weight ratio, for example. Sorry. Okay. In this case, we can also be very aggressive. We can say reduce the mass by 70% if we want. Of course, we will see what are the results and we can leverage those results. So let's say that we can do this kind of thing. Also, we can add manufacturing controls like preserved region, for example, points, faces that we want to preserve for the from manufacturing point of view. Also, we can specify the mold direction. What is the mold direction? Basically, if we have in mind a classical way to produce this thing, we have a mold, or let's say we are dealing with a fusion of these materials, so we have a preferred direction. So it's possible to say that, to preserve that. Okay. So also now we can see the final shape. The final shape here is based on the mesh itself. As you saw, there are no dimension, no parameters that have already defined. So we have just defined the volume that we want to start, from which we want to start, and we can define how much we want to reduce the mass. Also, we can leverage, let's say, this kind of slider to check more or less if we want, let's say, a lighter approach or a heavy approach, and so on. Also, in the end, we can also export this mesh to another configuration, for example, to another part inside SOLIDWORKS, and we can have both approach, so we can use it for, let's say, a more classical approach dealing with cutting, for example, at a CNC machine, or we can deal with an additive manufacturing like the 3D printing. So the goal now in topology study is based on the real life conditions. Let's say you have to set up an analysis like in simulation, and so it's based on what you expect to be used on that product. Also, you can optimize the form, the shape of the product, and you don't have any limit, any boundary here, because you are not defining any parameters. Also, you have the support either for additive or subtractive manufacturing. So if you want, you can export the mesh like that and just polish that for 3D printing. Or if you want, you can use it as a base for redefining the design. Okay, let's go on. I would like to have at this point a poll from you. So which the level of interest that has raised this webinar. I kindly request your participation. Okay, let's check some other seconds. Okay, perfect. So I would like also to share the results with you. Okay, perfect. So thank you very much for your feedback here. Just let's go on. Okay. So I would like also to ask, sorry, if you want to be contacted for further information. So please answer also to this poll. Okay, perfect. So I close this poll and I share the results. And thank you again for the feedback. Okay, so let's talk about now. Okay, for the next episode, we already spoke with Alessandro. Let's talk about the next year. We have an idea in mind I would like to share with you. Basically, we are thinking about, let's say, helping your work with, let's say, improve in productivity and results. So if you want to get advice from us, you can send us your simulation. And of course, we would like to have the most interesting case shown for the your personal trainer series for the next year, for the second season, let's say. Of course, we will require to sign a waiver. This is not meant to be a consulting activity. We like to just to improve your work, to give you feedback and suggestion. Of course, we would like to focus only on current simulation customers. And here are our feedback, our emails to have your feedback. And I think we are done because there are no questions at all. So if you would like to input some question, we are ready here, or you can, of course, write to us. Also, you can check on my YouTube channel, Alessandro Bellini SolidWorks. It's about simulation and all the webinars that I've already recorded in the past. And again, you will receive this this webinar recording in some days through your email. So no questions so far. So I thank you for your participation and have a good evening. Thank you, and to next webinar. Bye-bye.
Thank you. Bye-bye.